I thank you for asking. I'm going to enjoy learning something. That's what I think. And so, thank you very much. Dr. Nichols and I have been talking about senior research projects here recently. And a few of the difficulties for us as faculty members, we're going to be starting on it, is that we are to have 3 people on the committee and then an advisor. And sometimes if we have enough students, we're going to have difficulty because we don't have enough professors. And so, I'm asking people to do it, for the individuals who work under me. Other people are asking, basically say, well, when are we going to schedule it? I don't know, how about I'm going to say this, Megan, I was thinking we have 2 sessions for you. I was thinking about it for a little while. Yeah, we do it twice. I was going to call it an encore presentation.
Do it twice?
Yes, I was thinking about that. And then one of the professors said, what are you trying to do to this student? Enough's enough, So he said, don't worry about it. I don't have to see it. That's what one faculty member said. I'd like to see what happened. Maybe she could just tell me what the conclusion is, that type of thing. I'm interested. But she didn't have to show it all to me again. I said, oh, no, she will.
Oh,
yes, that's right. I just wanted to see how it ended. Anyway, that's enough of that. We are gathered here today to help get prepared for the test number 2. Don't forget test number 2 is scheduled tomorrow. Several of you might be taking the test around 4 o'clock, a few of you will. And so that's wonderful too. I'll be in the office at that time. We had last time had a study session which has been posted online, and it dealt with, many of you were here, it dealt with learning the definitions and the statements of known theorems. And so today what I want to do is maybe remind ourselves of those definitions and statements, but we do it maybe through practicing some proofs that could be asked of you, as well as going over some particular typical problems that you can expect on. So that's what I want to do today. So I'm going to start, even though we did it last time, in terms of the proofs, where I will ask at least 2 of the following, so I'm looking at part 3 of that study guide. Let's start off with that Bolzano virus test. So this is a statement for which I would just write, if I ask you this problem, just state and prove it, okay? So I wouldn't give you the statement. I'd say, here's the name, you say what it says, and you prove it. And so we have to be able to say what it says. This was something we went over last time, but just because we go over it, just because we know it at some point, I'm a person, I forget things, okay? You may forget things. Can anybody say what the Bolzano virus stress proof says? Mariah, can you say? Hi. Thank you, Melissa. Every
subsequence.
It has subsequence in it, but not at the beginning. Every
Sequence.
it has a certain characteristic. Every adjective sequence.
Monotone.
No. Every bounded.
Every bounded sequence has a convergent subsequence.
That's correct. Okay, we did this statement and proof last time. Let's do it again. It's easy to have some difficulty remembering things, okay? This is one that you hope I ask, and then it's short. Okay, so every bounded sequence has a convergent subsequence. It's also a good one for me to ask, not only because it's short, beneficial to you maybe because of that way, but it involves a lot of other big ideas, some named theorems. So if I ask you this one, you've got to quote some other theorems. Okay? So here's the proof. We let x of n be a bounded sequence. Okay, So it's a bounded sequence, right? So we want to show that it has a convergent subsequence. So what we do is we say, since, well, it's not, it's that from the monotone, that's what it's called, monotone subsequence theory. So wait a second, what's the monotone subsequence theory? What it says is that every sequence has a monotone subsequence. So there exists a monotone subsequence of x sub n. We're going to give it a name. Say x sub n sub k. All right, so that's the monotone subsequence, x sub n sub k. Well, what do I know about x sub n sub k? It's a subsequence of x sub n. What do I know about x sub n? It was bounded. So if x sub n is bounded, any part of it is also bounded. So since x sub n is bounded, then x sub n sub k is bounded. Thus, so I'm just going to write something to be very, clear. What can I say about x sub n sub k? Well, it's a bounded monotone sequence. And what do we know about every bounded monotone sequence? It converges. How do we know that?
By the monotone conversion.
So x sub n sub k converges by the monotone converges. And I'm going to say that's it. Why is that it? Well, I was supposed to show that x sub n had a convergent subsequence. Well, there it is, x sub n sub k. It's a convergent subsequence. Yeah. That's it. So, look, I can do the proof. That's why I'm your teacher. Okay? That doesn't mean you can do it. So, how come I can do the proof? Well, there's several reasons why I can do the proof. First of all, I've been teaching the class 10 years. So I've done it a bunch of times. So that helps me. And so I think that that's right. I have the experience of going over it again and again and again and again. And we need to get that experience, or getting that experience is helpful. So I'd like to help you get that experience just in a short period of time. First thing is, let's try to remember, what are we talking about? We're talking about the Bolzano boundary. What does it say? Every bound, we're talking about bounded. Every bounded sequence has a convergent subsequence. So that's what it says. Every bounded sequence has a convergent subsequence. Okay. Every bounded sequence has a convergent subsequence. I say every bounded sequence has a convergent subsequence. I know the Bolzano Weierstrass there, and it says every bounded sequence has a convergent subsequence. That's what it says. That's what it says. Okay, well, how come? Well, okay, here's the reason. If you give me a bounded sequence, then what I know, just because it's a sequence, it has a monotone subsequence. That monotone subsequence is going to be bounded. And because it's a bounded monotone sequence, it converges by the monotone convergence theorem. I'm done. Okay? I just have to write that up. I was wordy in what I wrote up here. But really, it's 3 steps. You give me the sequence. Okay? It's got a monotone subsequence. Maybe 4 steps. That monotone subsequence is bounded, and thus it converges by the monotone convergence theorem. Because what does the monotone convergence theorem say? It says every monotone sequence converges. No, a monotone sequence converges if and only if it's bounded. A monotone sequence converges if and only if it's bounded. That's what we use. What's the monotone subsequence theorem? It says that every sequence has a... No, what is a monotone subsequence?
Monotone subsequence.
Yeah, every sequence has a monotone subsequence. That's what it said. And you say, well, how am I supposed to remember this? Well, you remember we did a problem. Remember I gave you something like sine of n times pi over 4 or something like that, or cosine of n pi over 4. And I said, find a monotone subsequence here. And it had to have one. That's what the theorem says. Every one of them's got one. Is that okay with everybody? Well, why don't we spend some time, just a little bit, somebody else trying to prove it? Okay? Just somebody. Somebody besides John or Megan. Just, I can do this. Or I'll try to do it. Audra, will you try to do it?
I'll try.
All right, there we go. That's a good attitude. So we just spend just, and don't, here it is. Let me erase it. Let me erase it really good. Read what's down by the imprint. Oh, yeah. As I erase the board, I want to thank you for showing up. I think it's nice, maybe it's out of fear, but I think it's nice that you show up and work with me. That's nice. That's part of why each one of us are teachers. We enjoy working with people. Okay, so we enjoy that. So thank you very much. I want to state the theorem. I get out of your way. You state the theorem. You say how the proof goes.
Oh, man. Am I being recorded?
Yeah,
Oh, shoot.
you're going to be a video star.
Oh, boy.
I mean, I've had a lot of trouble dealing with fame.
Well, don't let me go on then. All right, the Bolzano-Weierstrass theorem states that every...
Write it down. Yeah.
Okay.
You see, we already got problems. Her handwriting is much better than mine. Already.
Every monotone sequence has a bounded convergent subsequence.
Every bounded.
Bounded. Goodness gracious. Well, I told you not to let me do it wrong.
Okay.
Convergent.
Yes, ma'am.
Is that electrical?
Yes.
Okay. All right. Proof. Let Exodus be a bounded sequence.
That's right.
So by the monotone,
Audra, may I help you?
yes, please.
Read the theorem.
Every bounded sequence has a convergent subsequence.
So you're trying to find a,
Convergent subsequence.
so first
I know
thing,
there's one step in between.
right, so you want to get a, what do you want to get? You want to get a conversion,
Oh, I need a subsequence.
so you need a subsequence. I mean, the theorem's telling you what to look for. So how are you going to get a subsequence? What subsequence do you want to look at?
Exodus, okay.
And what's so special about it?
It's,
You won't show it's convergent, but what kind of step are you going to make in between?
I know how something to do with the monotone.
That's right. By the monotone subsequence
Okay.
theorem.
There exists a monotone subsequence. the monotone subsequence theorem, there exists a monotone subsequence of exaben, say exabens of k.
All right, good. All right. So what do you know about exhibits of K?
Well, it's a monotone subsequence
That's
of
right.
exaben.
That's one
Now
thing.
I'm going to the monotone convergence theorem.
And what does the monotone convergence theorem mean?
It means
What does it say? It says that a monotone sequence is convergent.
it can only if it's bounded.
So you better say something about exhibits of K being.
It's bounded. Since
Ah,
exaben-
there you go. I'm gonna move the camera.
Go ahead. Ooh, and this is supposed to be, no, it's
Don't let Audra be working and you not.
It's,
Since
since
exhibit,
exaben is,
bounded.
exabens of k, well,
since exhibin is bounded, then
exabens of k also has to be
right.
bounded by the,
Now, it has to be bounded because it's a subsequence of a bounded sequence.
okay.
It's part. So I just say exhibits of K is bounded.
That's by the,
You're on the right path.
that's by the monotone convergence theorem.
You're looking at exhibits of K, a monotone sequence that is bounded, thus it must,
Then it converges.
okay, what's it?
Exabens of k.
That's right. And that's the proof. Is that okay?
That's okay. That's my favorite part.
Mine too. Mine too. Why don't we spend just another few minutes having somebody else do it? Okay? Calvin, will you give it a try? You think it to do it? Okay, let me erase it so nobody can see it. It's okay there.
Gotta take my notebook up there.
I would rather you didn't. You said, oh, you can. Oh, you're playing. I'd rather you didn't. You can do
At least when I'm doing it on my paper, I can stare at it for a little while.
it. You know, I want to say this. It's writing it here on the board is not the same thing. I'm going to say this other thing, Calvin. Let me bother you as you come up. Writing it on the board when you're videotaped is not the same thing, okay, as writing it while you're just at your desk. Anyway, there was a class that I was teaching that was online, and nobody would be in here, and I just lectured. No, there's nobody in the room, and I would get nervous. There's nobody in the room, and I would get nervous because I was being videotaped, and I knew no one was here to catch my mistakes. If I wrote something silly, you know, just a sloppy mistake, it was there forever. I didn't like that. All right, so Dalvin's giving us the statement. What's the Bolzano virus trust deal with? It deals with bounded sequences. What does it say about them? They've got a
Convergent.
subsequence. That's what it says about it.
Right, so every bounded sequence has a convergent subsequence. So let's, oh, let's again. You gotta say a bounded sequence?
Yes, sir.
Monotone.
That's right. That's right. Uh-huh.
Sorry, I'm not the best report writer.
You're doing great.
There's this. Okay. Oh, shoot.
Yeah, that's why it's called that name.
Subsequent. Since accident is founded, accidents, okay, is founded.
That's right.
So that's founded since accident, okay. And monotone. Monotone. Conversion.
That's right. That's right. You're doing perfectly. It's fantastic. That's it. It's fantastic. Okay? Exactly. And I don't know how you feel about it, but that is the way that I feel about it. When I get it done, I'm thinking I can do it. You know? Yeah. So that'd be a good one, Dalvin, for me. Here's what I'd like to tell you. If you can get it, get it. So, and you can get it. There's nobody in this room that's incapable of learning this. There's nobody in this room who can't do it. But some of it takes longer than others. It takes me a little while to learn things. So we just have to put in the time. That's what we do. Not that we can't do it. It's, do we have the time to do it? And the will to do it. Okay? So that's something important too. And I'd love to be at home watching some TV show. So well, I'm not going to do that. I'm going to do this instead. Okay. So let's go ahead to the next one. And what I'd like to do from now on is probably I'll just prove them and scream at you what I'm thinking. And maybe that'll help you in terms of learning it, for those of you who need it. The next one is the sequential criterion. For function limits. And so if I ask you to state and prove this, that's what I'll be asking. If I ask about this in terms of its proof, I'll be also saying state it. So we've got to be able to state it. So here, I'm reading it. It's talking about sequences and function limits. So both those are going to be involved. Okay? So that's what. So if I'm talking about functions and their limits of functions, then I know what the setup's going to be. So first of all, you've got to talk about the domain of the function. So you say let A be a subset of R. Okay? Let, we got a function. F goes from A to R. And we're going to be talking about a function limit. Where do we have function limits? Oh, we have it for C elements of A. Nope. That's right, cluster points. That's what we're talking about, cluster. let C be a cluster point variable. Okay. Then the following statements are equivalent. What are they? What they are is that the limit as x goes to C of f of x equals to L, and that's equivalent to the following statement. If x of n is a sequence that's NA with x of n being different than C for all n elements of the natural numbers, and the limit as n goes to infinity of x of n equals to it. Then what's that force acting?
Limit as n goes to infinity, f of x of n
Okay.
equals L.
So the output values, that sequence, that has to go to L. Those two statements are the same. A lot of times I'll just write down f of x of n converges to L. I won't write it in that limit form, but that's what we mean. That's correct. That's a correct statement. Okay, so we want to prove this. All right, so I said I would do it. So here's what I remember as I move the camera. It's an if-only statement. The two statements are equivalent. So one implies two and two implies one. One implies two, I think. We'll start off here with the setup. So let A be a subset of R, F go from A to R, and C be a cluster point. Okay. So here in this direction, we're going to assume, we're going to let the limit as x goes to C of f of x equals L. What do we want to show? Well, we want to show the second statement, okay? We want to show that anytime you give me a sequence that's NA, none of its terms are C, but it converges to C, then f of x of n's have to converge to L. That's what I'm saying.
Suppose x of n has that property.
Right, so let x of n be some sequence NA with x of n different than C for all n known natural numbers, and the limit as n goes to infinity of x of n equals to C. So what I'm writing here, Mary, is just the setup. What is it that I'm trying to show? This is what I got to show two. What's two? It says, well, anytime you give me a sequence that's in A, none of its terms to C, but it converges to C, we want to show, so here's what I want to show. F of x of n converges to L. That's what I want to show. I'm talking about a sequence of numbers, f of x of n. Now I want to show it converges to L. That's a number. How do I show a sequence converges to a number? Well, I'm going to use the definition for a convergent sequence. What is that? That's the one that involves epsilon and? No. Don't let me bother you. No.
I'm sorry.
Is that to be sorry about? Okay. It's a sequence. Is that okay? Don't let me bother. It's a sequence. When sequence, we got epsilons and? When we got sequence, we got epsilons and? Okay. Is that all right? No problems. Don't worry about it.
Hieroglyphics.
Let epsilon be greater than 0 be given. We need a k on the natural numbers such that for all n bigger than or equal to k, what's going to happen? The absolute value of f of x of n will be less than epsilon. That's what I'm looking for, this k. Okay. Well, here's what I know. First of all, since the limit as n goes to infinity of x of n equals to c, I know I have a k. I'm gonna write it. Okay. Then, there exists a cap, on natural numbers, such that for all n greater than or equal to k, or I don't think I've done it the right way. Here's what I think. This is true that I'm going to have a k, right? But I haven't done it in the appropriate order. So what did you say? I can make the sequence be as close to C as I want, but I didn't do it the way I wanted. So I need to back up.
We'll go back here.
Instead of picking out about the x of n, which is going to be k, let's concentrate on this first. Let's try. So since the limit as x goes to c, f of x equals to L. That's what we're assuming. Sorry. So we pick on that part first. What does that mean? We've been given an epsilon. So now we do use the fact that there's going to be a delta, right? Then there exists a delta greater than 0, such that for all x element of A with 0 less than x minus c less than delta, then absolute value of f of x minus L will be less than epsilon. So that's what I have. So what does this say? It says, hey, as long as you're close enough to C but not equal to C, then the output values are within epsilon units of L. Well, I want certain output values to be within epsilon units of L. Which output values do I want to be within epsilon units of L? The f of x sub n's. How can I guarantee that happening? I need to make sure that x of n's are within delta units of C. How can I make sure that the x sub n's are within delta units of C? They are, if I push far enough along in the sequence, because the sequence converges to C. So that's what I'm writing next. So since x sub n is a subset of A, so every x sub n is in A. You see this? So that I can apply the above statement. Every x sub n is in A. And x of n is different from C for all n element natural numbers. That means the absolute value of x of n minus C is always going to be greater than 0. So this part is going to be satisfied. And the limit as n goes to infinity of x of n equals to C. And I've been given an epsilon, so there exists a k. I got a k. That's a natural number, such that for all n bigger than or equal to k, x of n minus c will be less than delta. That's what I want. So the x of n's are minus c are less than delta, and I know that means the output values, f of x of n's, will be within epsilon units of L. But that only happens if x of n's are never c, which they're not, and x of n's are in A, which they are. And so here's what I got. So for all n greater than or equal to k, because of this right here, and this implying this, we have the absolute value of f of x of n minus L will be less than epsilon. Here, I'm just replacing the x's by x of n. Because the x of n's I'm talking about fit this. So, the limit as n goes to infinity of f of x of n's equals to L. That's the first part of the proof. Not easy. Got several steps.
It makes a lot more sense now, pointing out where things match up.
I'm glad. That's what it is. Well, now we want to show 2 implies 1. To show this backwards direction, we will show the contrapositive. So what's the contrapositive? So we're supposed to show that 2 implies 1. What's 2? 2 is about the sequence. Every sequence in A, that none of its terms are A, but it converges to C. If that has the property that f of x sub n converges to L, then that's going to imply that the limit as x goes to C equals to L. So that's what we're supposed to be showing. What's the contrapositive of that? Contrapositive of that is, so if 2 implies 1, the contrapositive is not 1
Was not to.
implies not 2. That's right. Okay, so what is not 1? Not 1 is that the limit as x goes to C is not
L.
L. Is that all right with that? That's 1. Let's write that down. Here, we're going to suppose the limit as x goes to C of f of x is not L. So what that means is that the definition of the limit as x goes to C of f of x equaling L is violated. Okay? It means that it's not true. It's not true that for each epsilon there exists a delta. Okay? Such that for all x is really close to C but not equal to C, then the output values f of x will be really close to L. And so it's not true for all epsilon. So if it's not true for every one of them, what does it mean to not be true for every epsilon? Hey, it's not true for every epsilon. That means there must be one that it's not, at least one that it's not true for. Does that make sense? So if it's not true for them all, there's got to be one that's not true for. So here's what we say. The way that we write the opposite of the definition of the limit of a function is, so there exists an epsilon not greater than 0, such that no matter what delta you gave me,
For all delta.
so for all delta greater than 0, there exists an x, well, maybe we call it x of delta, element of A with, it satisfies the normal things. 0 is less than x of delta minus C is less than delta. But the absolute value of f of x of delta minus L will be greater than or equal to epsilon naught. So that's what it means to be the opposite of the limit as x goes to C of f of x. It's not L. What it means to be the opposite of the conversion to L. So I have to write that down. Okay? So that means no matter what delta you give me, no matter what, there's an epsilon so that no matter what delta you give me. Well, here we look at several deltas. So we know there's this epsilon. Okay? We got it. Doesn't matter what delta is, no matter which one you do. Consider deltas of the form 1 over n.
Letting n run from 1 to infinity.
Where n is an element of the natural numbers. So, there exists, if you will, so for delta equal to 1 over 1, or just 1. So right now, I know there's epsilon naught. Here's a delta. I know that for every delta, here's 1 that's positive. There's some guy in the domain of A that's really close to C, but the output value is not so close to L. So there exists an x of 1, it's called. Element of A with 0 being less than x sub 1 minus C being less than delta. 1. But f of x of 1 minus L is bigger than or equal to epsilon naught. Well, I don't just do this for n equal to 1 for my delta, but I do it for n equal to 2. I do it for each n. equal to 2, we have an x of 2 on the base with 0 less than x of 2 minus c less than 1/2. That's where n is equal to 2, okay? And the absolute value of f of x of 2 minus L is greater than or equal to epsilon naught. I'm gonna do one more, just to drive home the point. For n equal to 3, there exists an x of 3. Where is it? It's in A. With what? What properties does it have besides being in A? There's 0 less than x of 3 minus c is less than 1/3. 1 over n. N is 3. And f of x of 3 minus L, again, is greater than or equal to epsilon naught. We continue this process forever. Or for each n element natural numbers. Thus, we have created a sequence, x of n's. Where is each x of n? It's in A. So this sequence is a subset. And each x of n has this quality. Okay? So how do I write that generically? With 0 less than x of n minus c is less than
1 over n.
1 over n. And that's the value of f of x of n minus L is greater than or equal to epsilon.
And that's the proof, right?
Very close. So I'm just going to write some kind of conclusionary statements. So we've got this sequence. So I want to make sure, John, how you said that you lied, that I went through and showed
That's fine.
that everything
That's very helpful.
matched up. And so here, yes, it is the proof, but I just wanted to emphasize, okay? So here, thus, we have an x of n in A with, okay, I know the people at home can't see this, but the fact that 0 is bigger than the absolute value of x of n minus c means x of n is never 0. Oh, you know that. And the fact that x of n minus c ends up absolute value is less than 1 over n. That forces the x of n's to converge to c. But because the f of x of n's are all of them stay epsilon naught units away from L, then that says that the limit as n goes to infinity of f of x of n is not L. So we've proven not 2. Is that okay? So not 1 implies not 2. And that's it. Kind of long. Kind of long. Anybody want to ask me anything about it? Here's what I remember that helps me get the proof. Okay? So I want to tell everybody, if you memorize it, fantastic. I don't have anything against that. Good. That helps you. We want to see that you say, I know what's happening here. It's hard to memorize things when you don't know what's going on. So you get more power to you. I don't think you can memorize it all. But what we're looking for is, can we understand is what people say. Oh, I think that's fine. We should. But I don't think any of us and just say, oh, I can just prove anything from thin air. I don't think any of us can. I think most of us have to have some little prompts. So here's my prompts for this. So I'm trying to tell you something to help you remember. Here's my prompts. First of all, I know what it says. The forward direction, 1 implies 2, okay, is a direct proof. Okay? It's a direct proof. And it's based on the definition of a convergent sequence and the limit of a function. And if you wanted to remember something about the forward direction, is that after you write down what you have to show, the first step, which I didn't do, remember I had to go back and correct, would you concentrate on the limit as x goes to c of f of x equals L. You concentrate on that first. And then you talk about the x of n's converging to c. Is that okay? That's the order. I didn't get the order right. Remember I had to erase it? That's one thing in the forward direction. The next thing I remember is the backwards direction is a contrapositive. And then I just let it lead. And what I remember is I have to write down the opposite of what it means the limit x goes to c of f of x equals, but it doesn't equal L. So I have to write down the opposite of what it means for the limit x goes to c of f of x equals L. I have to write down the opposite of that. I did that over here on this side of the board. That might be something for you that isn't easy. You might have to spend some time going over that. But it takes time to learn that when you say the opposite of for all, okay, you're saying there exists. Instead of saying for all of them, you're saying there's one, at least one. Okay? And when you say there exists, the opposite of that is for all. And so remember, in the definition of limits x goes to c of fx equals L, it says for each epsilon, for all of them, there exists. We say exactly the opposite. There exists one epsilon such that for all of the deltas. Exactly opposite. So anyway, you got to write that up right. And then what you do is you concentrate on deltas being equal to 1 over n and form a sequence in the domain. Okay. None of it's all in A, none of its terms are C, converges to C, but F of that does not converge to L. That's contradicting this part too. All right, anyway, that's what I had to say about it. Does anybody have a question? You have a question, Megan?
I have it written differently.
What do you have it written as?
Well, when we consider like delta be equal to 1 over n, well after that I had then there exists an x of n element of natural numbers such that x of n is an element of A, and then I wrote the 0 and stuff, and then I put, like I didn't show like the x of 1 or x of 2.
So if you just say, therefore for deltas equal to 1 over n, we're going to get x of n's that are elements of A with x of n minus c is less than, it's greater than 0, but less than 1 over n, and f of x of n minus L is greater than or equal to epsilon. If you just say that, then you say, yes, we formed a, yes, that's good enough. Here I was trying to emphasize, here's how we're forming the sequence. So I was giving, in this description, I'm giving more detail. How are we getting that sequence? I'm doing x of 1 for 1 over 1. I'm doing it for x of 2 for 1 over 2. Okay?
Is x of n an element of naturals or
A.
of A or
A. No, it should just be A.
just A? In my notes.
So if I said that x of n is an element of natural numbers, n is an element of natural numbers. X of n is an element of A. So if I wrote that, I made a mistake. Thank you very much. Okay, so that's that proof. So the next thing we want to do, and that was long, the next one we want to do is about if x sub n is Cauchy, then it is bound. That's what we want to do. Let's see if we can get that. So here's the theorem. So if x sub n is a Cauchy sequence, then x sub n is bound. We're gonna simply improve it. Okay. Okay. So for the proof, we let x of n be a Cauchy sequence. We want to show x of n is bounded. Okay, so I'm just going to stop for a second, let that sink in. Calvin, come right next to you. Okay, wait just a second. What the heck does it mean? I said, listen, we write things down, we read them. What the heck? You know, why are we writing things down? We're writing things down so we look at it. What does it mean to show x of n is bound? How do we show a sequence of, I gotta know what it means to be bounded. What does it mean for a sequence to be bounded? It means there exists a m greater than 0 such that x of n inside absolute values is less than or equal to m for all n element natural numbers. So I've got to produce this m. So we need, let's write that. What is it we're talking about? We need an m. Greater than 0. You can say greater than or equal to, okay? We're greater than this, but greater than 0 such that for all n element natural numbers, absolute value of x of n is less than or equal to m. This is so stupid, so I tell it to you. I always think of this movie, The Lord of the Rings. We need one M to bound them all. And that's what they said. Didn't they say that? Isn't that right? Am I saying something stupid? Didn't they say that in the movie? Didn't they say about for a sequence they need one M to bound them all? Isn't that part of the movie? It's that guy that played Magneto. He says it. Thank you very much. That is what I think.
That makes me happy.
I'm glad.
The worst part is I have a friend that's a Lord of the Rings nerd, and she's not a math major, so.
Well, she should be.
She'll
A lot in
never
common.
understand that.
Now look, this just fell on the board. I can't put this in my mouth because there are people here. I can't stand it. I thought what a good piece. Okay. So how am I going to get this in? Well, the only thing I get to use, I say this phrase, but I mean use. I say the only thing I get to fight with, I'm not fighting against it. It's fighting alongside of me trying to get this proof done. Is that I'm assuming that x of n's are Cauchy. That's the only thing I got. X of n's are Cauchy. So, what does it mean to be Cauchy? Let me say it and then use it. It means to be Cauchy. So x of n is Cauchy. It's if for each epsilon greater than 0, there exists a k, element natural numbers, such that for all n and m bigger than k, the absolute value of x of n minus x of m less than epsilon. Okay? And so that's what it says. It says for each epsilon you give me, well, I'm going to give you one. I'm going to give you a specific one. I'm going to give you one. I don't have to. It could be 20. I'm just going to look at 1. Epsilon equal 1. Since x of n is Cauchy, then by definition there exists k element natural numbers such that for all n bigger than or equal to k, absolute value, not for all n bigger than, that's wrong. For all n and m bigger than or equal to k, absolute value of x of n minus x of m is less than or equal to 1 in this case. Well, I've got two variables, m and n, running around. I'd like to fix one of them. And so what I'm going to do is fix m. I'm going to say let m be equal to k.
Did you do the less than or equal to so that we can?
No, I made a mistake. Should be just less than.
Okay.
Made a mistake. Okay, so because it says for any m and n, I want to fix m. So I'll say thus, for all n greater than or equal to k, what we have is x of n minus x of k. So I fixed k, one guy here. He's going to be less than 1. So x of k is a specific term in the sequence. Okay? It's a specific one. It's not moving around. I got that guy. Okay, so that means that minus 1 is less than x of n minus x of k, which is less than 1. So, I just rewrote that. Mary left us, I was about to say something to her. She'll notice it when she gets back. This is that absolute value statement. Rewriting the inequality with absolute value. That's something Mary's doing in her senior research project a lot. So, if I try to solve for x of n, remember what I'm going to say something about is the absolute value of x of n. So really I want x of n in the middle. By itself and to the right I want something positive and I want its opposite on the left hand side. Is that okay? That's what I'm looking to do. But I've made a mistake here. See? I wish Mary was here. I made a mistake. I wrote this statement down, but this isn't true all the time. It's true for
N bigger than or equal to k.
okay. For all n bigger than or equal to k. That's what it's right. Okay? It's not true all the time. So, if I add k to both sides, it's minus 1 plus x of k, less than x of n, less than 1 plus x of k. Why am I doing that? Because I want x of n by itself in the middle. When is this true? For all n greater than or equal to k. Okay. So, here, I don't even know the 1 plus x of k is positive. It's so easy to look at this and say, oh, here's it's positive, this is kind of close to its negative, not quite maybe. We don't even know if this is positive. X of k could be minus 7. So how do I make it positive? What I'm going to do is I'm going to use the absolute value. So I'm going to say minus 1 minus the absolute value of x of k. That just got smaller than this right here. Is less than x of n, which is less than 1 plus the absolute value of x of k. That's true for all n bigger than or equal to k. Wait a minute. That gave me a negative of a positive and x of n in between. So that lets me write down the absolute value inequality. What do I get to say? So the absolute value of x of n.
Less than absolute value, or 1 plus absolute value of x of k.
Right.
For
Hey.
all n bigger than or equal to k.
And that's the part that doesn't tell me that. That's the part that tells me I'm not through. Because I don't want it to be, I don't want to have a bound just for the n's bigger than k. I want to have a bound for all the n's. Not just the ones bigger than k. Okay? But we're close. Well, here's what somebody knows. They said, well, look, if you've got a bound for all of them beyond a certain point, you're bound to most of them. The only ones that aren't necessarily bounded by this are just the first few.
K minus 1.
K minus 1 times x of 1, x of 2, x of 3. Well, that's just a few of those. So just find the maximum between the absolute values of those and this guy. So here we're going to let m equal to the max, biggest value of x of 1 inside absolute value, x of 2, all the way up to x of k minus 1, all the way up to 1 plus the absolute value of x of k. Because this bounds the rest of it. Then, for all n known in natural numbers, absolute value of x of n is less than or equal to 1. And that's the proof. Megan, I want to thank you again for finding that mistake in my statement. Okay? But the x of n's being element of the natural numbers. That's a good thing to find. And thank you all. Is that okay with everybody? Okay, that's that proof. Any questions? Yes, ma'am.
Why don't we have to use the ends? Like, could you do it also with the ends instead of the ends?
Yes. What
Okay.
it was, Audra, is this. Down here. Down here, I'm having M's and N possibly changing, moving around. And I thought, well, gosh, if we have the M's and N's moving around, it's tough just to isolate the X and N. Because it's going to maybe change as M changes in terms of a boundary. So I'd like just to fix it. So how do I fix it? Well, this statement right here is true for all N and M bigger than or equal to. It's true for all of them. So why don't just isn't it true that if you let M be K, isn't K bigger than or equal to? Okay. So K could be one of the M's. Let it be one. Let it be the M. So let's just fix that. And then I don't have to worry about X of N's moving around. Is that okay? Okay, well, let's look at the next statement. This okay then? Yep, go ahead, Megan.
Do we have to like when we integrate it from zero? Like, can we just go after we say when we should found? Can we go right to let epsilon?
You can go right to let epsilon. I'm writing some things down that may be not necessary to remind me what to do. Okay? Megan, let me say this to you. We should write down enough to convince the person we're talking to. So you guys are going to be talking to me. That you know what you're doing. That's number one. That it's clear. And number two, I'm not doing that. Okay, for you. That's not what I'm thinking necessarily. What I'm thinking when I'm up here, so this is a kind of semi-confession, is that just because I've taught this thing 10 years in a row doesn't mean I can't forget something. And so when I'm up here, every once in a while I'm thinking, what is it I got to do? And so I write down little baby steps to remind myself, this is what I've got to do. And that baby step helps me. That's good. I got to walk out that door. I made it. It may not look like I'm getting there fast, but then I'll see you get warmed up and you can try out the door maybe. But if you're stunned and don't know what to do, take a little baby step. Let me start doing something. Okay. The next theorem that I want to look at is about if the limit of x goes to c, so here's the theorem, proof. If the limit of x goes to c of f of x is 0, then it is unique. Okay, so this is analogous to the theorem that if you have a sequence of real numbers and it converges, what it converges to is unique. It only converges to one thing. It's very similar. Okay? So the proofs are similar to the way that I presented them. Okay? And so you know how I said I need something sometimes to prompt me? So here's what I remember Mariah's prompt. It's a proof by contradiction. I remember that one thing. It's a proof by contradiction. So I just put that in mind. So I'm going to say, suppose the limit as x goes to c of f of x is not unique. So what does it mean to be unique? To be unique means there's only one. It's like Highlander. To not be unique, there's at least two. So that is, suppose suppose there exists L1, L2, element of all, with L1 different than L2, and the limit as x goes to c of f of x equals to L1, and the limit as x goes to c of f of x equals to L2. So I got two limits, let's say. Well, one thing we're assuming is that L1 and L2 are different. And so if they're different, one of them's got to be bigger. And so I don't know which one's bigger. It doesn't matter. One of them's bigger. And so what we say is, without loss of generality, assume, so one of them's bigger, that L sub 1 is less than L sub 2. Okay? That's what I'll say. So, that means that L sub 2 minus L sub 1 over 2 is greater than 0. And that's going to be playing the role of my epsilon in the definition of a limit. Now, wait a minute. How do I know L sub 2 minus L sub 1 over 2 is greater than 0? Here's the reason I know it. The first reason I know it is that L sub 2, we're assuming, is bigger than L sub 1. What does it mean for L sub 2 to be bigger than L sub 1? It means that L sub 2 minus L sub 1 is an almost positive number, which means it's greater than 0. So the top's greater than 0. We've proven that natural numbers are greater than 0. Is that okay with everybody? So this too is greater than 0. So we got two positive numbers being divided. That means we get a positive number. Okay. So here's what we got. Since the limit as x goes to 2, x goes to c, of f of x equals to L sub 1. Let's concentrate on that. And I've been given this as like my epsilon, okay? Then there exists a delta greater than 0, such that for all x element of that, with 0, if we're talking about a limit, 0 less than absolute value of x minus c less than delta. So I got this delta. Let's call it delta sub 1, because it works for L sub 1. Then, the absolute value of f of x minus L sub 1 will be less than this positive number, L sub 2 minus L sub 1 over 2. So I'm going to work with it for a little while. Okay, I'm going to work with it. So, let's remind ourselves what we're talking about. We're talking about the x's in A with 0 less than x minus c less than delta sub 1. What do we have here? We have, well, rewriting this as an inequality without absolute value, we have minus this. Minus this is L sub 1 minus L sub 2 over 2 is less than f of x minus L sub 1 is less than L sub 2 minus L sub 1 over 2. So, for all x element of A, with 0 less than x minus c is less than delta sub 1. Okay? Well, let's get f of x by itself. So I'd add L sub 1 to both sides. When I add L sub 1 to both sides, I get 3 L sub 1 minus L sub 2 over 2 is less than f of x is less than, when I add L sub 1 over here, I get L sub 2 plus L sub 1 over 2. That's what I get. Okay, I'm good with that. That's the statement I want to stop at about the L sub 1. But now I'm going to do the same dang thing, except I'm going to be working with the limit as x goes to c of fx equal to L sub 2. So I'm going to do the exact same process.
3
Okay, so thank you very much, first of all, for asking. What did I do to both sides? I added L sub 1. L sub 1 is the same thing as 2 L sub 1 over 2. So I have a common denominator. It's okay? Yeah. I'm done. Yeah, that's right. There isn't any mystery. Sometimes maybe there's not enough details for us to follow it perfectly, but there isn't a mystery, okay? We can answer it. Okay, so since the limit as x goes to c of f of x equals to L sub 2, there exists a delta sub 2 greater than 0, such that for all x element of A with 0 is less than x minus c is less than delta sub 2, then absolute value of f of x minus L will be less than, again, L sub 2 minus L sub 1 over 2. So now I'm going to say, hey, about the x's we're talking about, and then I'm going to rewrite this inequality. For the x's we're talking about, what x are we talking about? So, for all x in A, with 0 less than x minus c inside absolute values is less than delta sub 2. Here, rewriting this as an inequality without, compound inequality without absolute values, I'd have L sub 1 minus L sub 2 over 2 is less than f of x minus, I forgot to write something here. What should I have written? That's right, Mariah. L sub 2. That's right, I made a mistake. Good. Okay, so, for all x element of A, with 0 is less than x minus c is less than delta sub 2. We have, I'm going to add L sub 2 to both sides. This says L sub 1 plus, well, it'll be plus, L sub 2 over 2 is less than f of x is less than, here, I'm going to add L sub, so it's 3 L sub 2 minus L sub 1. This right here, that f of x is bigger than this particular number, and over here, f of x is less than that particular number, are contradictions. Except we're not in the same situation. Remember, this situation is for x minus 2 inside absolute values is less than delta 2. Over here, it's for x minus, minus c, not x minus 2. X minus c inside absolute values is less than delta sub 1. So what we do is we say, let delta equal to the minimum of delta sub 1 and delta sub 2 to force both of these inequalities to be true. So to be really close to C. Okay, so to make sure that you're as close to C as you need to be. Then, for all x element of A, with 0 less than absolute value of x minus c is less than delta, we have both statements. Mariah, here's how you can tell that I don't have the proof memorized, that I can spit it out like a printer. Here's how you can tell. I need to leave these on the board so I can look at them to say, I know what I want to, I know what I can say. If I erase them, I get, oh, what was it? That's why I have this work here, so I know what to do. So I'm going to leave this on the board just a little bit. So what I'm thinking is for all x in A, such that 0 is less than the absolute value of x minus c is less than delta, then we have two statements. This one down here, right here. We have 3L sub 1 minus L sub 2 over 2 is less than f of x is less than L sub 2 plus L sub 1 over 2, and this other statement over there. So I have to look. So it's over here. Where is it? It's that guy right over the far right, next to the last line. I think it says that L sub 1 plus L sub 2 over 2 is less than f of x, which is less than, I think it's 3 L sub 2 minus L sub 1. Maybe I do have it memorized. Did I write down the right thing? I didn't have to look, but I do have it memorized. But that's what I'm looking at. Okay? That is where I'm looking. And look, why are these contradictions? They're contradictions right here. This is happening, and at the same time this is happening. But they say exactly the opposite. Okay? It's a contradiction. So if you're looking at a contradiction, which is what we are, what does that mean? It means we didn't make a mistake with our logic. We must have made a mistake in what we were assuming. That's right. So that means our assumption is wrong. What was our assumption? It was that there was more than one limit. So there can only be one limit. I'll say it this way, at most, one limit. So if it exists, it is unique. Is that okay with everybody? Mary, this proof reminds me of your senior research project, a lot. Where I'm writing absolute value statements and translating them. That's what you do a lot in your proof of L'Hopital's rule. You know, Mary, we go from here to here. Okay, anyway, that's the end of the thing. What's next? Well, first of all, is there any question about what we did? Yes, sir.
At one point, you say X is the element of A.
Yes, sir. For all X element of A.
I don't really say what A is.
A is the domain of the function. You're right. You're right.
Is it okay to do that?
Commonly,
I think that I'm taking some liberties. If you write that down, yes, it's okay. What I'm not writing is that the setup. What's the setup? So here's the setup. The theorem should say this. Let A be a subset of R. Let F go from A to R. Let C be A plus. I'm not writing that.
Okay.
I'm not writing that jump down.
Okay.
I'm saying we know that that's what should be there. Is that okay? That's what we're talking about. But that's right. You're right. I'm not being as formal as what I could be. Not saying, hey, look, who's that? And if you don't, that's okay too. On this one, I said. Okay. All right. Well, anybody else with a question or comment? Anybody else want to say something? Ask about something. Okay. Then let's do the next one. Okay, what's the next one? The next one is to prove this. Here it is. It's an algebraic property for limits. It says if the limit as x goes to c of f of x equals to L, and the limit as x goes to c of g of x equals to m, then the limit as x goes to c of f of x minus g of x equals to L minus m. What do I think of this? I would describe this as we're saying this is an algebraic combination of functions. So It's a theorem about limits of algebraic combination functions. Okay. And before I go to prove this proof is easy. It's based on something now. So let me turn the camera so we know what we're talking about. This is the statement. Okay. So what is this based on? Remember, we have related limits to, say it again. Limits of functions to sequences. That's right. That's what we related. How have we related them? We related them to a big fact. What was the name of the fact? That's right. The sequential criterion for function limits. Okay? So let's remember this. So before I do the proof. Okay? So I'm going to do the proof. When I write down proof, I'm talking about the proof of this. But let's recall the sequential criterion for function limits. So let me write them. All right, can you say it? And this time, Dow, let's don't eat slide. Oh, he's having a good time, you know. Oh, yeah.
F, go, beta R, and C, B, A, plus the point. Okay. The following, or
That's right.
the following equivalent if, or no, not if, it's one, the limit is X goes to C of F of X equals L, and two, if F, or if X is in, and then goes from 1 to infinity, stole.
All right. Melissa? I like that. Dalvin, that was a real gentleman there. Yeah, thank you for laughing at my joke. Dalvin said, okay, go ahead. I don't get anybody else to play. Go ahead. All right. You sit down. Okay. Melissa? Mary? John?
NA.
With Dalvin?
X is in 9 equal to different from C.
And?
The limit is N goes to infinity of X of N equals C.
Then, what's that fourth acronym?
Then, the limit.
You can say that.
Oh, okay.
You can say it. So the limit is n goes to infinity.
N goes to infinity of F of X of N equals,
Yeah, it's on the board.
then it equals C.
No.
No, I knew that.
L.
L.
L. Melissa spoke.
L. Thanks.
You're welcome.
Now, it's hard. I want to tell you, it's just hard.
Walk to it. This one in particular.
I want to tell you, people, you know, we talk about, oh, we want to be good. It's hard. We want to be good teachers. Oh, we are a teacher. It's hard. Okay? It's not easy. I can do everything perfectly. It doesn't matter. As long as I don't do anything wrong, it's up to you from now on. I mean, I can help you, I can encourage you, I can scream at you, I can say, go ahead, you can do it, you can. But it's up to you to put it in. I can show you examples, but it's hard. It's not easy. All right, so why am I writing that on the board? Because that's what we're going to use. So here, I want to prove, let me change the camera. Be careful there. Okay, so proof. This is of that theorem. So we're going left, the limit as x goes to c of f of x equals L, and the limit as x goes to c of g of x equals to 10. We want to show the limit as x goes to c of F minus G acting on X equals to M. Okay. So the way that I'm gonna do this, the way I'm gonna show this, is use the sequential criteria for function limits. So how am I gonna show that the limit, I didn't write this right. It should be
L minus.
okay, L minus. How am I gonna show this? What I'm gonna show is this. You give me any sequence in the domain A, such that none of its terms are C, yet it converges to C, then F minus G of that sequence better converge to L minus M. And if I can show that, then we got it. The limit is L minus M. So on the left, X of N. What X of N am I talking about? I'm talking about the ones that fit here. Okay? That's exactly what I'm going to write. X of N being the subset of A, with X of N being different from C, and the limit as N goes to infinity of X of N equals to C. Okay. Then, I'm going to look at it directly. Then what about the limit as N goes to infinity of F minus G acting on X of N? So this is a sequence. Okay? What about that guy? Well, wait a minute. By definition of F minus G, that's the first thing we use. This equals the limit as N goes to infinity of F of X of N minus G of X of N. Now note, since the limit as X goes to C of F of X equals to L, then by the sequential criteria for function limit, just for that guy, just for that function, the limit as N goes to infinity of F of X of N, that equals to L. Well, I could say the same thing, except for F, I could say it for G. That's right. All right, on this one. Similarly, since the limit as X goes to C of G of X equals to M, then by the sequential criteria for function limits, the limit as N goes to infinity of G of X again equals to M. Okay. Thus, I'm going to repeat myself a little bit. The limit as N goes to infinity of F minus G acting on X. We already said that was essentially the limit as N goes to infinity of F of X of N minus G of X. I already said that. But now we're talking about a limit of functions. A limit, not a function, limit of sequences. And what I know is not only a limit of sequences, this is a sequence and this is a sequence, and what we do between those sequences, we are subtracting. We have a previous fact about sequences. That if you've got a sequence that converges, you've got another sequence converging, you subtract them, that forms a convergent sequence, and what do they converge to? They converge to the subtraction between the limits. So this is the same thing as equal to the limit as N goes to infinity of the first guy minus the limit as N goes to infinity of the second guy, which equals to L minus M. So what we have then, or since I'll say, since the limit as N goes to infinity of F minus G of X of N, where what do we know about X of N? There was something in that? None of his terms are C, and it converges to C. And since F minus G acting on that is equal to L minus M, then for any arbitrary X of N satisfies those three conditions, then by
Sequential criteria for function limits again.
right, the limit as X goes to C of F minus G acting on X equals to L minus M. I'm done. I'm done with that. Listen, it's not enough to watch me do these things. You gotta be thinking about it, going over them, trying to get the main idea. Trying to be able to produce them yourself. Making sure they make sense to you. You know, as I say that, I want to tell you, it makes sense to me that if I were to eat less and exercise more, I'd lose weight. One thing for it to make sense is another thing to be able to do it. I'm having difficulty. Not easy for me. I like eating. So it takes some effort. And we eventually, some of us eventually get there. Okay? So I'm eventually trying to get there. But it's not easy. So it takes effort, okay? So you gotta work. All right, the next theorem says the following. Sequential criteria for continuity. Okay, so here it's an if and only if statement. I got to state it. I'm going to break the setup. Let F, let A be a subset of R. F go from A to R. And C be an element of A, because we're talking about continuity. Then, F is continuous at C. If and only if and only if, for each sequence in A, but this time it doesn't say what X of n is being given to C. Doesn't have that. With the limit as n goes to infinity of x of n equal to C. Then, f of x of n, what does it converge to? It converges to L. That's wrong. That's right. It's not L. Converges to, that's right. Okay. So a little difference here, maybe. I'm just thinking I can just quote the words or whatever. I better be thinking about it. Okay. That's what it said. See if we can prove it. It's an if and only if statement, so I'm going to go in this direction. I'm not going to write the setup. Here's what we're looking at. We're looking at F is continuous at C. We're going to let x of n be a sequence in A with the limit as n goes to infinity of x of n equaling to C. What do we want to show? We want to show the limit as n goes to infinity of f of x of n equals to x. That's what I want to show. I want to show that the sequence converges to something. Okay. All right, how do I show the sequence converges to something? We're gonna let, that's right. Let epsilon be greater than 0 to be given. What do I need? We need a, that's right, element natural numbers, such that for all n greater than or equal to k, the absolute value of f of x of n minus f of c will be less than epsilon. That's what I want. How am I going to make the output values be close to f of c? Yeah, how am I going to do that? Well, the reason I won't be able to do that is because f is continuous to c. Since f is continuous to c, there exists, well, I've been given epsilon, so there exists a delta greater than 0, such that for all x element of a, with x minus c being less than delta, then this tells me that the output values f of x minus f of c will be less than epsilon. You know, I'm going to stop for a second. I'm going to go over this for just a second. I want to tell you something. Just what's on my mind. I think I have inside of me a partialness, an ism. I'm an Alabamianism. So I have preference for people from Alabama. So I guess it's anti-discrimination or favoritism for people from Alabama. So having said that, I want to tell you about the greatest teacher of all times in terms of the last 300 years. Okay. It's Helen Keller's teacher. You know what I'm talking about? This lady who was blind, deaf, can't speak, learns sign language, if you will, some symbols to represent things. Now think about this. This is like the anti-marathon. So if you can jog just a few steps, that doesn't mean you can run a marathon. Eventually you get tired, maybe you stop. Just because you can do it once doesn't mean you can do it forever. Well, this was the anti-marathon. Just because you miss it once doesn't mean you miss it forever. I don't know why they're putting these symbols in my hand, making my hand wet. Why is somebody doing that to me? That must be what that lady's thinking. They're playing a game for years. Teacher doesn't quit. I said that must be the greatest teacher in the last 300 years. It just keeps on going. Also must be the greatest student in 300 years. Because they don't sit there and just say, oh, it's a game. One day, that student says, wait a minute. You're saying there's a connection between these. And then that poor lady that was a teacher has to start making the connections between everything. What's the symbol for this? Because all of a sudden the student got excited. Does that make sense? So just because we're missing and struggle with it, don't get it, doesn't mean we quit. We keep going. We're not going to get it if we quit. We got to keep going, okay? That's my Alabama story for today. What is this? This says the following. Since F is continuous, what's that mean? That means if you get close enough to C, the output values are close enough to F of C. That's what this says. What are we trying to do? We're trying to say that the output values of F, where you're looking at the input values of X of n, will be close to F of C. How can we make that happen? We need to make the X of n's be close to C. Is that okay? How can I make sure the X of n's are close to C? But what are we assuming about the X of n's? They converge to C. So that means eventually they can be made arbitrarily close to C. Okay. So we've seen this kind of before. You know, as I erase the board here, finish up this proof, you might think in your mind, or might be thinking to yourself, I don't want you to think this. My God, there's 6 theorems and he's been working on them for 2 hours. How is he going to ask us a few of them and expect us to get them in an hour? I've been talking. I've been explaining. You guys are supposed to be ready to write them down, okay? And then it won't take that long. You have to think a little bit. It's not gonna take long, and I'm not gonna ask you 6. Okay, so let me think of something. You can do it. Okay, so what are we gonna say here? Well, since, I'm gonna say, go to the camera. Since the limit is n goes to infinity of x of n equals to c, and we've been given an epsilon, that means there does exist a k only in natural numbers. Well, forget the epsilon, such that for all n greater than or equal to k, I said forget the epsilon. Why? To ensure, go back over here, that the output values are close enough to f of c, you have to make sure that the input values are within, what's it say? Delta. So here, I'm going to say the absolute value of x of n minus c is less than delta. Is that okay? Thus, for all n bigger than or equal to k, absolute value of f of x of n minus f of c is less than epsilon. That's what it says. So the limit is n goes to infinity of f of x of n equals to f of c. That's that part of the proof. Oh, we got to go in another direction. Well, the other direction, okay, is we assume that anytime you give me a sequence in A, it converges to C, and that implies that f of x of n converges to f of c. That's the thing we're assuming. Suppose, all right, if x of n subset of A with x of n converging to c, all right, not that way. Then f of x of n converges to f of c. What do we want to show? We want to show f is, that's right, Alan. Let's see. We break this into 2 cases. Excuse me. About that, got on YouTube. Anybody remember what the 2 cases are? I'll give you a hint. It's based on C. What is it, Megan? If C is not a cluster point,
We don't have any work to do.
that's exactly right, John. Then F is automatically continues at C. Okay. What's case 2? That's right. All right. If C is a cluster point, how do we show continuity? Well, one way to show continuity if C is a cluster point, we know a fact that relates continuity to limits. Okay? So if C is a cluster point, F is continuous at C, if and only if the limit as x goes to C of f of x equals to f of C. So I want to show the limit as x goes to C of f of x equals to f of C. That's what I want. And that'll be enough. If I get that, that's good, because of C being a cluster point. That'll show continuity. Okay, well, how can I show a limit? Well, one way I can show a limit when I'm working with a sequence. Remember, I'm assuming about a sequence here. How can I relate sequences to limits of functions? Well, it's a big fact. Let's go. The sequential criterion for functional limits. Is that okay with everybody? So here it's to use the sequential criteria for functional limits, we let x of n be a sequence in A with x of n being different from C, and the limit as n goes to infinity of x of n equals to C.
Don't forget your for all in element.
Yeah, sure did. Sure did forget. Okay. What we want to do is we want to show f of x of n as a sequence converges to f of c. But wait a minute, that's what we're assuming over here. We're assuming more than what we need. Look, this says, hey, look, if you can show that for any time you give me a sequence in A, the number of terms are C, but yet it converges to C, that f of x of n will converge to f of c, then you got it. But what are we assuming? We're assuming that anytime you give a sequence in A, that x of n converges to C, and f of x, that implies f of x of n converges to f of c. That's what we're assuming. What we want is, we just want to talk about the sequences that converge to C that aren't, none of its terms are equal to C. What we've got is as long as it converges to C. So it includes these types. Is that okay? Okay, so finish it off. Oops. So, by assumption, we have f of x of n converges to f of c. So, by the sequential criterion for functional limits, the limit as x goes to c of f of x equals to f of c. Thus, since c is a cluster point, and we have this fact that if you looked at the cluster point, if c were the cluster point, this happened, then that implies that f is continuous to c. And that's the proof. Okay. Well, listen, I'm going to tell you that I'm pulling at least two of these from there. So if you know these, you know the definitions, you know the statements of theorems. We're talking about probably 2257 points. Let me tell you two other 16, 8 point problems. 16 points. We get up there over 57, 16, 63, 73. We're going to have a few multiple choice. Okay. Cluster point problem. Everybody got the cluster point problem, I think. Almost. On homework. Let me tell you two things from homework 5 that I'm definitely going to have on there. Okay? There's no doubt about it. So, I mean, it's going to be like this, okay? So, the limit of x goes to minus 3, 2x plus 5 equals to minus 1. I'm going to ask you something like that. What are you going to do? You're going to say let what do we need? That's right, John. Such that for all x in A. A in this case, Megan, is, what's the domain of this function? That's what it is. Yes, you can stick in any x value here and you get out something.
for all x over bar, with 0 is less than x minus, or minus 3, so it's x plus 3, is less than delta. Then, that forces 2x plus 5 minus a minus 1, so the function minus L, to be less than epsilon. So what do we want? We want this absolute value to be less than epsilon. That is 2x plus 6 to be less than epsilon. Good grief. We want absolute value 2 times absolute value of x plus 3 to be less than epsilon. We want, what do I want? We want x plus 3 to be less than, what do you let delta be? I'm done. And then the other proof is exactly the same type, except I'm going to show that f is, not limit, but f is continuous. I'm going to do the continuous. So continuous, that's what I meant. And I said it's, I should say, very simple. Okay, so let me just do a quick example. As I go to do this quick example, does anybody have a question for me? Anybody thinking, no, I wish you'd do this. Oh, I don't know. Well, I'm not kidding, Melissa. I'm going to ask something like this. Show f of x equal to 7x minus 12 is continuous at 1. At x equal 1. Mary experienced it. We say, oh, let epsilon be greater than 0 be given. What am I looking for, Dalvin? We need a bigger than 0. Such that, for all x, again, Megan, the domain of this function is R, so the A is R. With, oh man, absolute value of x minus 1 less than delta. It doesn't have that 0 that's bigger than here. For limits, it does. For continuity, it doesn't. Then, f of x, which in this case is 7x minus 12, minus, it's supposed to be f of 1, f of c. So what is f of 1? That's right. It's minus 5. It is less than epsilon. So we want 7x minus 17. Is that right? No. It would be minus 7, isn't it? Would be less than epsilon. So we want, well, you factor out 7, absolute value of 7, 7 times x minus 1 to be less than epsilon. So we want, I mean, it's an identical type of problem. We want x minus 1 inside absolute value to be less than epsilon of 7. So what do we let delta be? Epsilon of 7. I'm going to ask you something like that. So I'm thinking, 57, 8 more points probably for each one of those, something like that. So 16, 57, 63. That's like 73 points. Now we're not, at 73 points, we're not talking about a great score. But right now we're saying, hey. You know, we get some multiple choice, we get that cluster point type thing. We're now knocking on the door of having a very, very good score. Is that okay with everybody? All right. That's what I'm going to leave you with. That's what I got for today. You guys have a good evening studying, doing your jobs, okay? We'll see each other, for most of us, 1 o'clock. So others a little late. So. Yes, Dalvin said he would like to look at something about the cluster points. Why don't we take 2 minutes, or 3 minutes, 5 minutes, whatever it takes. So let's do just something else. About plus. Plus, we hadn't been here 2 hours. We've only been here an hour and 56 minutes.
So Dalvin, what do we mean by cluster point? We have to have a set. What does it mean for something to be a cluster point of set? It means this. The idea is the following. The idea is this. You give me a set, then the number is a cluster point of it. If no matter what little region I put about that number, it contains something from the set that's not the number. So my prototypical example is something like this. Let's let A be equal to minus 2 to 1, minus 2 to minus 1, open, closed, union to the sets of 1 over n. This is, let me write down what A is. Here's minus 2, here's minus 1. It doesn't include that guy. Open. It includes all of this, and it includes that guy. And then 1 over n, here's 0. 1 over n, the first number you get is 1. It's in there. Then you get a half, you get a third, then you get a fourth, fifth. And it just kind of works its way, as it is a monotone decreasing function, a decreasing sequence. It works its way towards 0. But does it ever equal 0? No. So if I were to ask you, is 0 in this set A? You'd say, no. Here's what I'll tell you. Is 0 a cluster point?
Yes.
Okay. So the answer was given correct. It's yes. And the reason is that about 0, so I'm looking here. Here's 0. Within the set. But remember, we got this sequence of numbers that are getting closer and closer to 0. So no matter what region I put about 0, eventually you got some of those sequence of numbers that get in there. And you say, well, what if you make this smaller? Well, you can. But eventually there are going to be some numbers from that sequence, 1 over n, that get in there. Is that okay? So no matter what little region I put about 0, there's going to be guys from A that aren't 0 that are in that region. So that's what makes it a cluster. There's things from A right up to 0. B. Is 1 a cluster point of A? But here's 1, Dal. Are there things from A right next to 1? No. Isn't there a little gap between 1 and something from A besides 1 itself? Yeah. I put this little gap about it. Does that have something from A that isn't 1 in it? That gap, that little region. What's your answer, Dal? No. And so that means this is not. So I didn't answer this guy. The answer was yes for this. And the answer for this is no. For me, that's it. That kind of example says it all. Is that okay? That one you Google it. I'm going to ask you something. Okay. The Cauchy problem, you know, if I put something like that on there, show that a sequence is Cauchy. Remember what we did in the example was the 1 over n. Okay? What I did in homework was to make something that was like 1 over n. Except sometimes we didn't recognize that. I wrote in your papers, hey, this is like that 1 over n problem. Some people tried to do it the same way as I did, but they made too big. They said the absolute value of the x of n minus x of m will be less than or equal to something. And what they made it be less than or equal to was too big. Okay, they made too big of a jump. So be careful, look at your notes there. All right, that's all I got.